This video is about mixed strategy, Nash equilibria, and zero-sum games. So first off, let's talk about the zero-sum game. So a zero-sum game is probably what you think about when you think about most games. It's a game where a win for one player is a loss for the other. So the games are strictly competitive. You can't cooperate at all. And usually there's no pure strategy Nash equilibria. Okay, so let's pause a second on the rest of this and talk about that. So here's an example of a zero-sum game, matching pennies. So two players each have a penny. At the same time, they choose whether they're going to show heads or tails. If the coins match, player 2 has to give player 1 $1. Okay, so player 2 is giving player, so in other words, player 1 wins and gets the money, right? Otherwise, player 1 gives player 2 $1, in which case player 2 wins, right? Okay, so this is a case, it's called a zero-sum game because it's just you either win $1 or you lose $1, right? So in this case, if they both show heads, player 1 wins. So they gain $1, but player 2 loses $1. If they show one of each, then player 1 loses $1, player 2 gains $1. Okay, so they're called zero-sum games because if you add up the payouts for any given outcome, it always adds up to 0. So it's called a zero-sum game. And with these kind of games, they don't typically have pure strategy Nash equilibria. Why? Well, a pure strategy is when you do the same thing every single time you play. And think about it, if you were playing this game with somebody, right, and I'm player 1, if I always choose to play heads, then you're going to know exactly what to do to counter me every single time, right? So that wouldn't be a good strategy for me. I don't want to just do the same thing every single time. I want to mix it up and sometimes do heads and sometimes do tails to get the best advantage that I can. Okay, so that when you do sometimes one thing and sometimes another thing is called a mixed strategy Nash equilibrium. Okay, so it's where a player should do one action part of the time and another player the rest of the, or another action the rest of the time at random according to a particular percentage. Okay, so you'll have like I'm going to do this 20% of the time and this 80% of the time, and I'm going to randomly do one of those things, but making sure that I kind of keep at those percentages. All right, and as a reminder, there is a rule with Nash equilibrium. Every finite game, so finite game is a game that stops. So as long as the game stops at some point, it has to have at least one Nash equilibrium. All right, so let's go back to our pennies game, right? So with this one, hopefully it should come off pretty instinctive to you. What would be the best strategy to win this game? Your best strategy here really would just be to flip the coin, right? Because you want to be unpredictable. You don't want the other person to know what you're going to do. Because if they know what you're going to do, then they're going to be able to counter you and make sure that they win. So you want to be unpredictable, okay? And you'd want to kind of evenly split between playing heads and tails. Why? Well, because if you're playing heads way more than you're playing tails, then your opponent's going to say, gee, they play heads a lot more often, so then I should do this to make sure that I'm going to win more often. Okay, so if you're doing more skewed one way or the other here, then your opponent's going to be able to counter you. Okay, so hopefully kind of instinctively you can grasp that with this one, your best bet would just be to flip the coin, right? 50-50 shot, whether you get heads or tails, and just randomly play one or the other 50% of the time. Okay, so this is sort of just an instinctive example. We're going to do the actual math out on how you would calculate these for a couple, but that's sort of instinctively what we're looking at here, is you're trying to figure out what can I do that is going to make it so that my opponent is not going to be able to guess what I'm doing. All right, so that's what we're going to calculate down here. So first off, a couple of definitions. We're going to use capital E, capital U to stand for the expected utility of a move. Okay, so basically what's going to be the expected outcome of a move of what I do. Okay, and then we're going to use sigma, this is a Greek letter sigma, to stand for the probability that a player does a particular move. All right, so you'll see this as we kind of write a couple of these equations. Okay, so let's start with this guy over here, and we're going to start by looking at what the expected outcomes are for player 2 playing either left or right. So I'm starting with player 2 playing left or right, and I want to know what is the expected outcome of that. Okay, so let's start there. So how I'm going to write this, I'm going to start with my first little equation. I'm going to say I'm going to find the expected utility of playing left. All right, well, what's the expected outcome if you play left? Well, if they play left, then every time that I play up, player 2 is going to get -3. Right? So I'm saying, okay, they're playing left, so I want to know what their outcome is going to be. Pink is left, so pink for these guys. right? So I'm saying, okay, every time they play left, their outcome is going to be -3 when I play up. So how I'm going to write that is I'm going to say, okay, every time that I play up, they get -3. So the probability of playing up times -3. And same deal, they're playing left. Whenever I play down, they're going to earn 1 point. So every time that I play down, they're going to earn 1. Okay, and I'm going to do the same thing with the right side. So if player 2 plays right, so I'm looking at the expected utility of player 2 playing right. All right, so in that case, every time I play up, they're going to get 2. So every time that I play up, they're going to earn 2 points. And every time that I play down, they're going to earn 0 points. So probability of down, they're going to earn 0 points here. Okay, so we've got kind of this setup here. So we've looked at what are going to be these outcomes for these ones. Now here's the thing that it took me forever to wrap my head around. So what I'm going to do is I'm going to use these two things to figure out not what player 2 should do, right? We set this up in terms of player 2's outcomes. I'm not going to use this to figure out what player 2 should do, though. I'm going to use this to figure out what player 1 should do. Why? Well, remember how we set up here, right? I want to make sure that I'm choosing heads and tails 50% of the time, but randomly, right? Because if I'm skewing more towards one or the other, right? If there's a noticeable favoring in what I'm doing, then they're going to know how to counter me, right? So it's the same kind of argument here. I want to set this up so that I'm saying that the expected utility of playing left is equal to the expected utility of right. So I'm looking at this and saying, okay, how should I play so that they are not going to care whether they play left or right, because it's not going to make a difference to their outcome, right? In this case, it would be 50-50. I want to play 50% of the time for each one of these because that's going to make them not care which one they select. Versus if I played like 70% of the time heads and 30% of the times tails, then they would definitely care what their outcome is, right? They would feel like, oh, I can skew my outcome if I do this instead, right? So I don't want them to feel like they can skew the outcome by changing their behavior. I want it to be that no matter what I do, they don't care what they're going to do, right? It's a balanced outcome for them because no matter what, they're getting the same outcome, okay? So what I'm going to do is I'm going to set the expected utility of playing left equal to the expected utility of playing right. And I'm going to use that to solve for what I should do, so what player 1 should do. So I'm saying, okay, I want player 2's outcomes of playing left or right to be the same because I am playing so well that they're indifferent to what they're going to do because no matter what, it's going to work out the same. All right, great. Now there's one extra thing that we have to pull into play with this. So we're going to set these two things equal to each other with just these guys. All right, but there's one extra thing, and this is a probability rule. Okay, so when we talk about doing something, right, probabilities always add up to 100%. So if I say that 70% of the time I'm going to do something, that means that 30% of the time I'm doing something else, right? Because the 70 and the 30 add to 100. Okay. If I say that I'm going to, there's a 80% chance that it's going to rain, that means there has to be a 20% chance that it doesn't rain, right? Because they add up to 100. So what I'm going to do over here, I want to get rid of one of these two variables using that fact. So what I'm going to do is I am going to use the fact that I know that the probability of playing down is equal to 1 or 100%, right? It's 100% is a whole number, minus the probability of playing up. So the probability of playing down is 1 minus the probability of playing up. And I'm just going to take that and I'm going to replace my probability of downs on both of these with this instead, just to get rid of an extra variable. Okay, so what I'm going to do, I'm saying the expected utility of left equals expected utility of right. So I'm going to set this equal to this. And along the way, I'm just going to sub that in for the utility for down. Okay, so first one is that every time I play up, they're going to earn -3. And every time I play down, but I'm not going to put in down, remember, I'm going to sub in this 1 minus every time I play up, right? Then they're going to earn 1. And I'm setting that equal to every time player 1 does up, player 2 earns 2 points. And again, subbing this in, 1 minus the probability of playing up, they earn 0 points. All right, and now I'm going to solve this equation, and right now you might be going, oh my gosh, this looks so complicated. We're going to solve this equation. It's really not that bad. It looks really scary at first, and when I first started looking at these, I was like, oh man, my students are going to hate this. But it's really not bad, okay? Because basically all this is these are variables. So as an equivalent equation, what we're going to do, this right here is like x times -3, aka -3x. This one right here is like a 1 minus x times 1. This is like x times 2, so 2x. And then this is like a 1 minus x times 0, right? So the steps that we use to solve this equation, we're going to do the same thing that to do this one, right? How would I solve this? Well, you technically would do a distributive property here, right? It's a 1, so it doesn't really matter. That's going to leave me with 1 minus x. And then over on this side, I technically do a distributive property, but it's just 0, so that's just going to go away, right? And then I'd want to group my x's together, so -3x minus x is -4x, right? And then I want to get all the x's on the same side, so I would add the 4x on both sides. And I get 1 equals 6x, so then x equals 1/6, right? So solving an equation like this isn't bad. We're doing the exact same thing, okay? These moves that we did here, we're gonna do the exact same moves for this guy, except instead of writing x's, our variable is the probability of up. Okay, so same deal, right? Writing this out. So with this guy, this would technically be a distributive property, right? And this guy would technically be a distributive property. We just happen to have really easy distributive properties. They won't always be. So this guy, if it makes it easier for you to write it as -3 times the probability of up, that's fine. And then this would be +1 minus 1 times the probability of up. Equals, over here again, you can rewrite that as 2 times the probability of up if that's easier for you. And then this multiplying by 0 is just going to go away, right? So that's gone. Then I'm going to group together my probabilities of up. So -3 and -1 adds to -4 times the probability of up. And then I'm going to get all these guys together. So I'm going to add that 4 to both sides and get 6 times the probability of up. And then I'm going to divide both sides by 6 to get the probability of up. So it's 1/6. Okay, so again, these steps are exactly the same, right? We're doing exactly the same thing here as we did here. It's just a weird looking variable. Okay, so we figured out that 1/6 was the probability of up. So what does that mean? So this is going to tell us how player 1 should play. So what this tells me is that player 1, because remember player 1 is choosing up versus down, right? So player 1 should play up, right? 1/6 of the time. And, well, 1/6 to get to a whole would be 5/6, right? That's the opposite. So they should also play down 5/6 of the time. And importantly, at random, right? So you don't want to just like, okay, the first time I'll go up and the next 5 I'll go down. And then the next time I'll go up and the next 5 I'll go down, right? Because if it's not random, then you're predictable and your opponent can counter you. Okay, so you want to make sure that you're being random when you're doing this. Okay, so that right there is how player 1 should play this game. So they should do 1/6 of the time they should play up and 5/6 of the time they should play down. So now let's go back and look at player 2. So we've done all of this for player 1. Now we're going to do the same thing for player 2. So it's going to feel exactly the same. We're going to come back up and come up with our expected utilities, but this time of up and down instead of left and right. Okay, so over on this side, I'm going to figure out the expected utility of playing. We did left and right before, so now we're looking at up and the expected utility of down. So we're turning our perspective. So now I'm saying, okay, if player 1 plays up, what's the expected outcome? Well, player 1, green, is going to get 3, right? Every time player 2 plays left. And they're going to earn -2 every time that player 2 plays right. Okay, if player 1 plays down, sorry, my cover-up method with my finger isn't really going to work well for this one, right? Then every time that you play down, when player 2 plays left, player 1's going to earn -1. So they get -1 every time that player 2 plays left. And every time that player 2 plays right, they're going to earn 0. Okay, so we're just setting that up. And now we're going to do the same thing we did before. I'm going to set the expected utility of up equal to the expected utility of down, because I'm going to use this to figure out how you should play left versus right. I want to play left versus right in such a way that it's going to make player 1 indifferent to what they do, because no matter how they play, they can't possibly get a better outcome. All right, so we're going to set this up, we're going to solve this, and I'm going to do a similar thing here, but instead of using down is equal to 1 minus up, in this case, I'm going to use right is equal to 1 minus left. Or you could do left is equal to 1 minus right. It doesn't make a difference, okay? So when I go to rewrite this, I'm setting this equal to this. So it's going to be 3 times the probability of playing left plus -2, not the probability of right. I'm going to write 1 minus the probability of left. All right, and then I'm going to set that equal to, this one is -1 times the probability of playing left plus 0, and then it's not times the probability of playing right, because remember, I'm going to plug in, ooh, I can't quite fit it, right? I'm going to plug in 1 minus the probability of playing left. Ooh, that didn't quite fit. All right, but it's okay, because when I go to solve this conveniently, we're multiplying by 0, so that's going to go away anyway. It's going to make my life a little bit easier. All right, so I'm going to simplify this. I'm going to do distributive property here, right? So this is 3 times the probability of playing left. -2 times 1 is -2. -2 times negative probability of left is going to be +2 probability of left. And then on this side, that's going to be -1 times the probability of playing left. That just went away, right? All right, so when I group my lefts together, so that's going to add up to 5. So I have 5 times the probability of playing left minus 2 equals -1 times the probability of playing left. I'm going to get all these guys together, so I'm going to subtract 5 from both sides. So I'll have -2 equals -6 times the probability of playing left. And then I'm going to divide both sides by -6 to get that probability by itself. So that's going to give me 2/6, aka 1/3. All right, and then there we go. So what does this tell me? Well, this tells me that when choosing left or right, player 2 should choose to play left 1/3 of the time. So player 2 should play left 1/3 of the time, and right 2/3 of the time. And again, it's at random. Okay, because if you're just doing it as a pattern, right, if it's always one of these and then 2 of these and then 1 of these and 2 of these, that makes you predictable. And if you're predictable, you're easy to beat. Okay, so in a game like this, a zero-sum game, you don't want to be predictable. All right, so we got through one example of how you'd figure this out. So let's take a look at a couple more. Okay, it's not going to be that bad. It feels like it's going to be a lot, but we're going to do this first one here, and then the second one we're going to kind of look at as a special case. Okay, so this is our stag hunt problem, right? So this is the one where we've got, you know, 2 hunters are going out to hunt, and they have to decide whether they want to go after a stag together or if they want to go jointly, you know, or separately and do rabbits or whatever, right? So this is not a zero-sum game, all right? And I can tell because 3 plus 3 does not add to 0, right? So that's what a zero-sum game should do. They should all add to 0, and they don't. So a mixed Nash equilibrium is not necessarily always a zero-sum game. They just tend to show up there a lot. Okay, so notice with this guy that even though this is our stag hunt, notice that I changed the words from stag and hare to up and down and left and right. That's kind of a default choice that we do a lot of times, is we use these words just because it's a lot easier to keep track of things. If you start using like stag and hare all over the place and you're using them for both players, it can just get really confusing to keep track of what's going on. Okay, so that's all that's happening here. It's nothing too fancy. It's just saying, okay, we're gonna do these different words. All right, so let's do the same thing. So I'm going to start by figuring out what player 1 should do. And to figure out what player 1 should do, you look at what the expected utility is for player 2. So I'm going to look at the expected utility of playing left and the expected utility of playing right. Okay, so if player 2 chooses to play left, then every time player 1 plays up, player 2 will win 3. So they're going to earn 3 every time that player 1 plays up. And every time that player 1 plays down, they're going to earn 0. So plus 0 times every time they play down. Okay, what about right? So if they play right, every time player 1 plays up, they earn 2. So they get 2 every time player 1 plays up. And every time player 1 plays down, they're going to earn 1. Okay. So then again, I'm going to take these two things and I want to set them equal to each other. So I'm setting the expected utility of playing left equal to the expected utility of playing right, because I want this player to be indifferent. They don't care which way they play, because no matter how they play, they can't beat my strategy. All right, so we're going to set these equal to each other. And again, I'm going to use that down is equal to 1 minus up. 1 minus up. So on the left side, I'm going to have 3 times the probability of playing up plus 0 times 1 minus the probability of playing up. And on the right side, it's going to be 2 times the probability of playing up plus 1 times 1 minus the probability of playing up. Convenient 0 is convenient, so that's just going to cancel out. So I have 3 times the probability of playing up equals 2 times the probability of playing up. And then distributive property here, plus 1 minus 1 times the probability of playing up. Okay, group these two together. 2 ups minus 1 up is just 1 up. And then I want to get all those ups together, so I'll subtract that from both sides and get 2 times the probability of playing up equals 1. So the probability of playing up equals 1/2. Okay, great. So what does that tell me? Well, player 1 should play half the time up and half the time down. So equally, half the time they should go after a stag and half the time they should go after hares, and they should just do that randomly. So this tells me that player 1 should randomly play up half the time and down half the time. Lovely. Okay, now let's go back and figure out the other player. So we looked at utility for left and right, so now we're going to look at the expected utility for up and down. Okay, so if player 1 plays up, then they're going to get 3 green, right? So they're going to get 3 every time player 2 plays left, and they're going to get 0 every time they play right. All right, and if they play down, then they're going to get 2 every time the second player plays left, and they're going to get 1 every time the second player plays right. All right, and it so happens with this particular one, if you take a look at these are exactly the same, right? It's 3 and 0 and 2 and 1, right? So when I set these two equal to each other and say solve it, you're going to get the exact same thing as you did over here. It's just at the end, instead of saying the probability of up, you're going to see it say the probability of left. Okay, so that is not always the case. It wasn't the case in our last problem, right? In our last problem, the numbers were different. This one had a -3 and a 1 and a 3, right? So they were different numbers, so you couldn't do that. But for this particular one, they happen to be the same numbers. So for this one, because it's the same, I can say it's the same thing. So in this one, player 2 should play left or right randomly half of the time each. That was terribly worded. I got partway through it and then I was like, this is a terrible sentence, but you know what I'm saying, right? It's the same thing as over here. Half the time they should do each one. All right, so that is how you find a mixed Nash equilibrium, okay? Now, one more I want to look at down here. So not all games have mixed strategies, right? We know that because some of them have pure strategies, right? So we've looked at ones before where it's like you should do the same thing every single time. And that's what's going on here, okay? So if we look at this game down here and we actually see, okay, well, what's happening here? Well, when you look at your options, player 1 should always play up, right? Because up strictly dominates down. So 3 is always better than 1, 4 is always better than 2. So player 1 should always play up, and therefore player 2 should always play left, because that's also their strict strategy, right? 3 is better than 1, 4 is better than 2. So for this particular one, this one has a pure strategy one, right? So this one right here would be my strictly dominated Nash equilibrium, and that should be my outcome. So if it does have one of those, it will not have a mixed strategy because it has a pure strategy, okay? So let's look at mathematically what's gonna happen when that happens. So like if you didn't notice that this had a pure strategy, how would you pick up on it by doing this problem? Okay, so let's run through this one again really quick. So I'm gonna look at the expected utility of playing left versus the expected utility of playing right. Okay, so if they play left, they're gonna earn 3 whenever I play up, and they're going to earn 4 whenever I play down. Okay, and if they play right, they're going to earn 1 when I play up, and they're going to earn 2 when I play down. Okay, we're going to set these equal to each other. I'm going to not write that. I'm just going to jump into writing this. So when I set them equal to each other, I'm going to have 3 times the probability of playing up plus 4 times 1 minus the probability of playing up equals 1 times the probability of playing up plus 2 times, again, 1 minus the probability of playing up. All right, so we're going to clean this up. I got a couple distributive properties here. So that'll give me 3 times the probability of up plus 4 minus 4 times the probability of up. And on this side, it's going to give me 2 and then minus 2 times the probability of playing up. All right, again, trying to clean these things up a little bit. So over here, the 3 and the -4 combines to -1. And on this side, 1 and -2 also combines to -1. And do you see yet what our problem's going to be? Ooh, sorry, slightly off the camera. Here, when I go to put these guys together on the same side of the equal sign, when I add this 1 to both sides, those variables are going to cancel each other out, right? So all of my probability of ups are going to cancel each other out, and I'm left with 4 equals 2, which doesn't make any sense. 4 does not equal 2. So when this happens, what happened is we got a nonsense answer. Okay, so we got a nonsense answer, and what that tells me is that there is no mixed strategy. I spelled that wrong. There's no mixed strategy Nash equilibrium. Okay, so this is what will happen if there is a strictly dominant one. When you try to solve for a mixed one, you're going to get something weird that happens here. Okay, so that's kind of what you should expect to see happen. So if you ever made this mistake, all of it would really mean is that you would do a whole bunch of extra work when you could have just quickly figured it out from the table. But you can still figure out that, oh yeah, this one would have a strictly dominant strategy.